This section will cover the basic concepts that are required to understand electrical systems and particularly the high voltage systems. In these few minutes, we will present an overview of all of the essential electrical properties such as the voltage, current, and resistance. Also, we will see how what are the relationship between these properties in a circuit, and finally we will discuss also what are the difference between the direct current and the alternating current. So let's first break down the key electrical concepts that are the voltage, current, resistance, and power. Here we have a general electrical circuit showing a representation of all of these parameters. And let's start with the definition of the current. When we talk about current, we are referring to the actual flow of electricity within our circuit. And if we create an analogy with water flowing through a pipe, the flow of that water will be equivalent to the current. It is the measurement at the end of the electric charge and the electrons that are going through a conductor, for example, a wire or a cable. The current is being measured in amperes, and the bigger the current, the more electricity is flowing. For example, in an electric motor, we need very large currents to be able to generate enough power to move the vehicle. On the other side, we have the resistance, and the resistance is what slows down the flow of electricity. We can think of the resistance like a very narrow section in the pipe of water that makes harder the water to flow through. In a circuit, we have materials that have very high resistance and let less electricity to pass through. The units of measurements of the resistance is the ohms that are represented with the Greek letter omega. For instance, wires with high resistance heat up more when we have high current flowing through them. Then we have the voltage, and the voltage is referred like the pressure that will pushes our water through a pipe, and in the electrical circuit it is the force that pushes the electrons or the electric charge through the wires. It is measured in volts. And for example, a typical electric vehicle has a battery that provides the voltage to the system that is between 400 and 800 volts. Without the voltage, nothing will move in the circuit. Without having that differential pressure is essential for creating the movements of electrons in the circuit. And finally, we have the power, and the power is a measurement of how much electricity our system is how much work the electricity is doing, and we can relate with the water flowing. For instance, if we use it to spin a water wheel, the energy that is being used is going to be related to the power. The power is measured in watts, and we define it as the product of the voltage and the current. So 1 watt is going to be equivalent to 1 ampere multiplied by 1 volt. For example, if we have a motor in an electric vehicle and this motor gets 400 volts and 10 amperes of current, the power that we are using is going to be equal to 4000 watts or 4 kilowatts. All of the previous concepts are connected and they are related between each other. And the Ohm's law, it's one of the most important principles in electrical systems because it states all of the relations between these concepts. The Ohm's law states that the voltage in a circuit is going to be equal to the current that is flowing through that circuit multiplied by its resistance. And over here we have the Ohm's law pyramid. This is a visual tool that helps us to simplify calculations for voltage, current, and resistance. And here we basically organize the relationship between these variables in an easy to remember format. So let's explain how we can calculate and how we can use this pyramid. For instance, if we have a circuit and we know already what is the voltage and what is the current, we want to calculate the resistance, the equivalent resistance of that system. What we do is to cover the variable that we want to solve. In our case, we cover the resistance. After doing that, the remaining formula is going to be that the resistance is equal to the voltage divided by the current. And in that way, we can resolve the circuit. Let's break down further in a basic example. That is the circuit that we have over here. If we know in this circuit what is the voltage and what is the resistance, we can then calculate what is going to be the current of that circuit. How we do it? Like using our pyramid, we will cover the current, that is the variable that we want to find, and we get to the equation that the current is going to be equal to the voltage divided by the resistance. As you can see here, after doing this calculation, and in this case as we have a voltage of 1000 volts and a resistance of 500 ohms, we can obtain that the current flowing through this circuit is going to be 2 amps. As we already have the voltage and the current that is flowing through the circuit, we can calculate as well what is the power of this system. And it can be easily calculated as the multiplication of both of those. And finally, in this case, we will have a power consumption of 2 kilowatts. Now, let's talk about the two types of electricity currents that we might have in the circuits. We can have direct currents or we can have alternating currents. These are the two main ways that electricity will flow in any circuit, and they are both crucial in the context of electric vehicles. First, we have then the direct current, and in this case, in DC, the electric charges flows in a single direction that is going to be consistently from the positive terminal to the negative terminal of a power source. In this case, in that figure that is shown over here, we have the symbol for a battery, and you can see the direction of the current is going to be from the positive to the terminal, to the negative terminal. Batteries, as was mentioning, is one of the examples of power sources that work in DC, but also we have, for instance, solar panels that also provide a DC voltage. Some of the applications that uses this type of current are the cell phones, portable devices, and the LED lighting, for instance. On the other side, we have the alternating current, and in AC, the electric charge will periodically change in the direction, and it will be oscillating back and forth. For example, here we have a representation of an AC current that has a sinusoidal waveform, but we can also have AC currents with square waveform, triangular waveform, or others. What is important here is that as this is a periodic waveform, we can relate also with the frequency of that waveform is one of the parameters. And for instance, in the case of the power transmission, we have a periodic a frequency in that signals of 50 or 60 times per second that is measured in hertz. AC is what is used then for transmitting electricity over long distances because it's very easy to convert to higher or lower voltages using simple transformers and also reducing the energy losses. And also this is the power that supplies our homes, for instance, from the electrical grid. Some of the applications also has or another source of AC power and AC current is going to be the wind generators that generate naturally the AC waveforms. Applications that use this type of currents, we have a lot of industrial processes that require AC to supply it, and most of our house appliances also required AC currents. In the context of the electric vehicles, We have the high voltage battery that provides the DC power, but often the motor is requires AC power to function efficiently. Also, in the context of the EVs, when we are charging the EV, we can use both of the types of currents. For instance, when we are having an AC charging, the vehicle onboard charger will be connecting the AC that is provided by the grid into the DC voltage that at the end will charge our battery. In the same way, we can also have DC fast charging. In this case, the charging station will supply the DC voltage that will be directly connected to our battery. Finally, let's discuss the conductors and the insulators. These are the materials that determine how electricity flows through a system and are critical in designing and operating high voltage systems. First, we have the conductors, and the conductors are the materials that allow electricity to flow freely through them. The reason is because they have many free electrons, and this material have a very low electrical resistance, which makes them excellent for transmitting electrical current. At the same way, these materials usually have very good thermal conductivity. Some common examples of conductors are, for instance, the copper, silver, the aluminum, even gold in some cases. From all of these, copper is widely used because, and is widely used in wiring for our electrical circuits because it combines a very good conductivity with cheap prices and with a high durability. In electric vehicles, for instance, conductors are crucial to ensure that the energy is transferred with the minimum energy losses in the system. On the other side, we have the insulators, and the insulators basically are the opposite of the conductors. The insulators resist the flow of electricity because they have all of the electrons tightly bound, and they are not free to move as easily as the conductor has, for instance. These materials then have a very high electrical resistance. Some examples on the insulators include, for instance, the plastics, the rubber, the glass, ceramic, and some others, but rubber and plastic are commonly used in the electrical cables to encase the conductive material and to protect against accidental contact to the conductive material. In high voltage systems, the insulators are critical for safety. At the end, the insulators prevent electricity from escaping of its intended path, and also protects the users and the equipment from the electrical shock and to manipulating the conductive materials. Here we are showing the structure of a high voltage cable. As you can see, it includes in the core the conductor. Then we have the insulating material, and as you can see, on top of the insulation there is a shield, and this shield acts as a protection against the electromagnetic interference, or EMI. Why this is needed? So, since high voltage cables carry large currents, these large currents create strong electromagnetic fields. Those fields can interfere with any nearby electronic component, or also can interfere with the same components that we have in our vehicle, and that cause operational errors and failures that we want to avoid. So this shield helps us to avoid the electromagnetic interference in our systems. And after, at the end, we have an outer shield also to cover our full cable. In the next slides, we will see then how all of these concepts and materials comes together to create the high voltage system